Now we have reached on lecture number 9 of module 2. In this lecture we will see that the transient stability for the multi-machine system. In previous lecture we saw that the equal area criteria for the single machine connected with the infinite bus system, and also we saw the various way to improve the transient stability. Those methods for improving transient stability, that is equally valid for multi-machine system as well. So in this we can, as suppose in multi-machine system there are m number of buses having n bus system. So if your generators is connected at the various buses and they are in m in number, then we can write the differential equation, the swing equation, for all the machines. Like here, it's a double differentiation of delta with respect to time. That will be equal to your pi f divided by hi. Hi is the inertia constant of ith machine. That is multiplied by the difference of your mechanical power input to ith machine minus the electrical power output of that machine. So this is the general swing equation for any ith machine. So we have to write the differential equation. This is a second order differential equation. So this I here will be start from 1 to number of, if there are m machines, so we have to write m equation. Now this PMI, to know this value is equal to your PG naught GI, means that is your initial power generation from the load flow that can be obtained ignoring the losses in the system. So the PM, that is a mechanical input to the generator at the internal voltage of the generator, it will be calculated by taking the PGI naught that can be obtained using your base case load flow, that will be PMI. So we have seen that this PM, that is mechanical power input to the alternators, that is assumed to be constant during your transient stability program. So this value is one fixed, and this PGI which is keep on changing, and that depends, because basically this PGI is your output of your alternator, and that depends upon the topology of the network. So now we have seen that equation, that swing equation here, it is your order 2. And we have also seen the various methods to calculate or to solve this differential equation. We have to have the single order differential equation. So we can just convert that differential equation into the two differential equations of the first order, and that can be done that we can take one variable, that is x1i here, because for every I we are calculating. I means number of generators. If it is m in the system, there will be m variables corresponding to x1i, and this x1i just we have taken as the delta I. That delta I is nothing but it is your angle of your EI, that is the internal induced EMF of IS generator. This is the angle of that one. Your second variable, that is x2 corresponding to ith machine, that is x2i, will be the derivation of your delta I, means this is nothing but your d delta I over dt, and this is, we know, this is nothing but it is your omega I. Now swing equation 1 can be written as a set of equation 2 and 3, and 2 is nothing one, I can write what is this delta I here, this is your delta I. So I can write here x1i, if you are differentiating this, so we are getting your x here, you can understand xi dot will be equal to your delta I dot, that is a differentiation of delta, and this delta I already we have from the here, we can say this is nothing but your x2i. So we have our differential equation corresponding to this one. Another one, if you are differentiating your x2i, that will be nothing but your double differentiation of your delta I, and this is nothing but your the differential equation, that the swing equation here, this is nothing but your this equation. So we can here write that x2I will be giving you this equation. So this is for all the machines you are going to get two differential equation if you are taking machine as a classical model. If you are taking the again very accurate modeling of generating system, then the differential equation will be changed and it will be of the different order. So here you are getting the two differential first order differential equation corresponding to each machine, that is alternator. So if it is m in number, then you have to write for all the nodes there. So to solve that we have taken the classical machine model. So this can be solved using the numerical integration technique, as already I have discussed, that we can solve either by modified Euler methods, Runge-Kutta methods, or trapezoidal integration method. To start any numerical integration technique, we require some initial guess, and that initial guess that we can have the initial guess for our transient stability program means your x1I is nothing but your delta, and delta that is delta naught, and this delta naught is nothing but the initial that you are getting from the load flow, this delta of individual machine, that is ith machine, that is a 0, that is not. So it is a pre-fault load flow that you can get. We also know that here, since this delta I is a constant, so your x2I it is nothing but your x1I dot, that is a dx upon dt, and this is here your di naught differentiation, means this is your 0. So this value will be 0. So starting with for all the machines, here I am talking for I, and this I is true for all the machines, and that is in m in your number. At the same time, you have to also select the appropriate time step of your integration. As I explained in the previous lecture, that this time step is very, very important, because this time step gives sometimes your less accuracy. If you are choosing this h in a different way, your solution may be unstable, and at the same time you may get inaccurate result as well. So the choice of this is also very important. If your step is very, very small, it may take more CPU time or computational time. So you have to judge, and it depends upon system to system. So at each step, the PGI has to be calculated. This PGI, that is a electrical output of ith machine, that can be easily calculated using the Y bus. This is nothing but your PGI is equal to your summation for all the buses, here AM, and here EI prime, EJ prime, YIJ cos delta I minus delta J minus theta IJ. Here this your YIJ is a Y prime I have written. This Y prime is calculated from the Y bus system. In this case, what we do, normally we eliminate all the buses except the generating buses for the different conditions, means pre-fault, post-fault, and the during fault condition. So if the system is reduced to eliminate all the buses except the machine internal buses, this can be achieved by ward reduction technique, that is very popular technique, and based on that we can only keep the internal buses or the generating units, and the remaining bus we can just eliminate, and then we can obtain the new reduced Y prime bus, Y prime, and that is here the element Yij is the element of this one. So it is for the fault as well as the post-fault condition. So we have to get for the pre-fault, post-fault, and the during fault conditions. To see how we can get this Y prime matrix. If your original matrix, that is Y bus, is here, I can again categorize, because in your system, let's suppose you have n bus. So in this n, you have m machine internal nodes, and remaining are your other nodes. So we can write this Y bus in here like this. So this matrix AA corresponding to all the internal nodes of the machine, and here AB is between other nodes with the internal, and so on and so forth. So we can form this Y bus as usual, that is used in the power flow analysis. only the difference in the Y bus here as well as in the load flow, normal load flow, that this Y bus includes load and the machine admittance as well. In this, as you know, in the load flow, we only take the impedances, admittances of the transmission line, transformer and the shunts. We never take the machine admittance as well as the load admittance. We take load as a PQ, we take machine as an injection of the power at the terminal buses. So here, a single machine, let's suppose your machine here, this is your generator. Now this generator will have some reactance and this is your VT. So we are having another node here that is called your EF or E prime, that is your excitation voltage. So this impedance is also included in Y bus and this is your JXD prime. So that is included here, but in the normal Y bus of the load flow we never include, but here we are including that one. So now if your N bus system, your system is having, let's suppose, N bus and it is having M machines, then your this Y bus matrix here just you are forming, it is nothing but your M plus N bus matrix, because here this is your number of buses in the system where generator is connected. We have extended one more internal bus. So it is a total number of Y bus order will be this cross this matrix. So that I am just emphasizing that here we are including the internal this machine admittance as well as the load admittance. If your load here, for example, at this bus is load is there, so we have to include this load into the its admittance form and that will be again taken into the account. So now our intention is to reduce this matrix to keep only this M buses, that is M cross M matrix, means we are only trying to keep this internal buses of all the generating system and eliminating all the buses of the system. So we have to eliminate this N matrix. So what we can do, this matrix element YAE minus YAB here, then inverse of this multiplied by BA, that will give your Y prime M cross M matrix, and that is called your reduced bus, and that is keeping only the internal load nodes of machine. In whole simulation, if there is any infinite bus is written, for that H can be taken very large, very huge value, and that can be even though taken as 1000. Now to see the transient simulation program how it will move, then you have to go for, first you have to run the load flow, and from the load flow you can get your this PGIs at all the generating stations. So after getting this PGI, then you have to model the components, the various components in the system. Then you have to list what are the configuration network changes, means during fault, post fault and the pre-fault conditions, and for each configuration you have to form Y bus for fault and the post fault condition. Then you have to solve the network solutions. Then you have to go for the dynamic solution of this whole dynamics of the system using the integration techniques, and again you have to keep on doing till your final convergence and final the time domain where you are going to simulate this. So the practical transient stability program should have detailed model of generating stations or generators, including the flux decay dynamics. Generally third or fourth order models are used. So even though there is higher orders of machine dynamics can be also modeled or treated, but normally we can go up to second or third dynamics of system. Also we have to represent excitation system in detail. This excitation system will have a different type of excitation systems are used for the different type of machines, so that will be also included in your practical transient stability program, because it is not only that you can model the classical model where we never model the excitation system, only we model the machine with the taking its inertia. So in the detail and practical transient stability program, we have to model the generators in detail, we have to model the excitation system, we have to model the speed governing system also as well, and we have to also go for the detailed representation of the loads. Because in the loads, there will be two types of loads. One may be your static loads, another may be your dynamic load. Dynamic load such as the motors. So the motor dynamics will be also included. If it is a static load, simple your P and Q loads, then you can model as a static. But the most of the the 80% of loads in power system is the induction motor loads, and that is a dynamic in nature. So that dynamics should also be included in the practical transient stability programs. If your system is having some other devices, for example, let's suppose FACS controllers. It may have your SVC, it may have your TCSC, that is a thyristor control series compensators, it may have the static synchronous series compensation, it may have the unified power flow controller. So we have to model these devices as well accordingly, and we have to take the dynamic model of these devices to see the transient stability program. If your system is having HVDC, then you have to also model the dynamics of HVDC accordingly, and this HVDC modeling, again we have to take the dynamics along with their controllers. We know this the FACS controller are very important to enhance the power system stability. It enhances all type of stability. It can be improving your transient stability, it can improve your dynamic stability, it can also improve your the voltage stability. So these devices are now coming into the practical power system, and they must be modeled accordingly so that we can see the detailed impact of the stability on the system. Dynamic model, let us see the dynamic model of synchronous generators. The dynamic model of generator includes its mechanical dynamics. Mechanical dynamics means again swing equation. Flux decay dynamics, again the representation, detailed representation of the machine itself. Then excitation system dynamics, that is the machine is equipped with the fast acting voltage regulators, AVRs, and then we have to model this excitation system dynamics, and also we have to model the governor turbine dynamics, because the governor of the turbine that gives the input to your synchronous machine, that may also work and it may change your mechanical input power. So if your study is for the particular long time, then this dynamics is also very important. So we have to include all these dynamics, including your mechanical dynamics, machine's flux decay dynamic, excitation system dynamics, and your governing system dynamics. Detailed models should include air gap saturation. Again, in this, your binding of machine may get saturated, so the saturation effect should also be taken into account. Field current limits, because there will be several limits, because field current cannot exceed certain values, as you know there will be field heating limits. So that limits, and also the line drop compensation, this is also used, that this compensation should not exceed that value. So all these models should also be included in this synchronous generator model. To see this mechanical dynamics, now we have to, so far in the classical model, we ignore the term, this is your single equation. Here, this term is nothing but this damping of the system. This is the generator load damping coefficient, that is a D, that is coming into the picture. In the previous case, we ignored this and then we solve the dynamic equation, that is a single equation of the machine. This is basically mechanical dynamics, because here the angle and machine's inertia constant, etc. are included. So now in the practical transient stability program, this is also taken into account, and that impact a lot in the transient stability and other stability considerations. So we can write the second order swing equation, including your m is the angular momentum, that is a double differentiation of delta with respect to time, then plus your damping coefficient, that is k d multiplied by speed, that will be equal to your mechanical power input to the alternator and your electrical power output, that is a function of your voltages, angles, theta. Theta is the basically admittance between your two I and J bus. Here Y bus element as well as your internal magnitude are the internal buses. So all these are included, this PGI. So this PG is the power output, that is electrical at the generator terminal. This PM is the net mechanical power input, and that is nothing but that is equal to your electrical power output of the generator at the internal node. What it means? This is your generator and it is connected with this terminal bus here, it is your VT. This machine can be represented by here EF, it is a impedance, and this is your VT. Now here we have E prime that is used, that is sometimes used EF, this is a field excitation. This is nothing but your JXD prime. So your PG is here, that is coming out, this PG is here, and your PM which is coming here, that is input to this, it is equal to that is coming at this here internal node output. If your losses are less are neglected in the machine losses here, so this can be equal to your the power output of the internal bus. So that's why here written the electrical power output of generators at internal node, that is here rather than here. It is your terminal voltage and that is your electrical output at generator terminal. So this is the difference between PG and PM. Now come to this flux decay dynamics, means detailed representation of machine itself. You know, this is a two fluxes are there. One is a rotor flux, another is your armature flux. Both are rotating in air gap at the synchronous speed, and the torque, that is electrical power, is produced due to the interaction of these two flux. So the flux decay dynamics is used in most of the cases. As I said, it may be your salient type of your machine, it may be your cylindrical rotor, where in the cylindrical rotor your XD will be equal to your XQ. This is the case when your machine is cylindrical rotor machine, cylindrical. This XD will be not equal to your XQ for your salient rotor type of machine, salient poles. So in that case your XD and XQ will be different. So what we can do is a very general, we can write the flux decay model for this type of machine, and wherever you want to use your cylindrical machine, if your machine is cylindrical, simply you put this value XQ is equal to XD, and then finally it is very easy that you can get the simplified equation from this general expression of the cylindrical pole machine. So to see this we have to use the various notations and nomenclatures. So that is a EQ prime. EQ is your generator internal voltage behind XD, and this is basically to the field proportional to the field flux linkage. Your EQ prime is the generator internal voltage behind XD prime. So this EQ prime is the internal generator voltage behind XD prime. Your E of D is generator field voltage E of D. Your ID is the D axis component of armature current. Phi is your generator terminal voltage, and TDO prime, here TDO prime, that is generator D axis open circuit time constant. Using these three, we can write the flux decay dynamics as follows. So here if you are using this, your TDO here TD prime O, we can write the differential equation in this fashion. So this is your E of D minus your EQ. Now this EQ here, this is a EQ prime ID, so we can write here, and that XD prime is normally very equal to your XQ. To this again you can see the several books, they have a detailed flux decay model. Normally we are going to use, so this equation can be again simplified using all this, and we can write here the TDO prime EQ prime, here we can get this equation too. where this VQ will be your XD prime ID plus EQ prime, and here this your EQ prime here, means using these we can from here we can get this equation. So we can simplify it using this and we can get this one differential equation here, that is equation number 2. Now from equation 1 and 2 form the third order model of generator. For the fourth order this model include the additional equation of here TDO prime, this one. If we are including this one, then it will be here another differential equation we are going to include. So if you are going to include this your third equation, and that additional equation if you are writing the differential equation for your here, that is a E D prime, then you can get the third order. Here it is a fourth order, means we are including this equation, so it will form a fourth order model of the machine. Now to get all these values here, this EQ prime, ED prime, thus they are related with the V terminal voltage as well, and this is nothing but we know this terminal voltage V is your VD square plus VQ square under root. So we can get these values, this terminal voltage we know it, and then again here we can, using these equations we can again solve the various equations. So all these equations are interrelated, and then we have to use them in your transient stability program. To include the air gap saturation, as we saw this in previous equations, there was no saturation was included, so this can be handled by correcting the expression of EQ by adding a saturation function, that is your SDEP. This SDEP is defined as some factor B and another factor is A. It is just related with V EP minus A upon EP, where A and B are the saturation constant. This EP is the voltage behind the Portier triangles. Again, when you will study the synchronous machine in detail, you will find this EP is your voltage behind the Portier triangle. Then this flux decay equation gets modified to here TDU EQ, this one. This is your one differential equation, and then here we have to put that value and then we can simplify it, and finally we are getting this expression. So where this is your XP is nothing but your Portier's reactance. To include the dynamics of excitation system, different model of excitation systems are existing, and again it depends upon what is the size of your machine. So there are various type of excitation systems are used, and again IEEE reports they have standardized that. So the 5 different standards model of excitation system is suggested. That is the first your type 1, normally we say. The type 1 is the continuously acting regulator with the rotatory exciter, means here we use the rotatory exciters. Your type 1S, that is your control rectifier with the terminal potential supply only. Your type 2 model, that is the revised excitation system, it is a brushless and saturation is taken into the feedback loop. Type 3 excitation system is your static with the terminal voltage and current feedback, and your type 4 is non-continuously acting excitation system. So type 1 exciter, this model has been extensively used for stability studies. It consists of measurement and the filter circuit, comparator and amplifier, excitation, that is a DC generator, and a feedback compensation, that is a rate feedback or stabilizing transfer function. It stabilizes the violent change in EFD. To see this, here just I want to show, this is your block diagram of IEEE type 1 excitation system. Here you can say this, as I said, it has several modules, several blocks. One is your measurement and the filter module, and the transfer function for this just can be written this 1 over 1 plus S, that is a Laplace transform S, multiplied by the TR, that is a time constant of the measuring system. That is coming here, and then we are using here V reference. means we are setting the terminal voltage, that is a reference voltage, certain value, and this is added with this reference, and then we are using another signal. This signal is nothing but other signals, like we can give some auxiliary signals from other sources, like we can use the power system stabilizers. Those are used to stabilize the power system. Those are used to improve the dynamic stability of the system. So that signal may come here. If that signal is not there, then it is 0. So that value is coming here, and then it is your feedback compensator is there, and that is here your EFT is coming back here, and then it is compared, and that error signal is getting amplified with the help of amplifier, and the gain of the amplifier is Ka normally represented, and it is 1 plus S Ta. Ta is the time constant of this amplifier. So it is a first order differential equation that it has been assumed for the amplifier. This amplifier will have some limiting value. So this value cannot be more than VR max, it cannot be VR min. If it is violating its limit, then we have to take its limiting value. Means here output is more than this, so that we have to set at this value. If this value is less than this value, then we have to set this, and then finally it will be given here to the exciter. This exciter time constant here 1 over Ke plus S into Te, and this will be your nothing but EFT. To include the saturation effect, this EFD here, that is going to be subtracted, because here we are taking the proportional value, whatever we are getting here signal directly, we are getting the EFD. But this EFD will have some saturation effect, then we can take this SE here, this function SE is a function of EFD that is going to be subtracted, and then this is a closed loop. And this EFD again is sent to here, and that is through the feedback compensator. And now that is coming to your generator, and this is the GS is your generator gain, that is GS transfer function, and then generator is giving your terminal voltage VT, and this VT is coming through your line drop compensator, that is a VC, V plus J I into XC. XC is your some reactance, and then it is coming here again to your measurement and the filter circuit. So this is your block diagram. So apart from other, it may have the following basic element, that is a voltage regulator, that is a voltage should not violate. So the exciter voltage ceiling limit, that's a regulated voltage ceiling, is a VR is also used. Line drop compensator is used before the measurement circuit to account for the line drop. In XC, the signal to measure the circuit is used this one, and of course the saturation of excitation. When excitation machine is loaded, its voltage drop due to the armature impedance drop and the saturation. So the saturation effect that I said we can take into the account. Here you can see this is loaded and without loaded. So the without loaded, here if your field current is increasing, the terminal voltage is this one, but once it is loaded, your terminal voltage variation is this much. So this is basically due to this saturation effect, and that should be taken into account for the detailed modeling of the machine. This is already explained, the block diagram of IEEE type 1 excitation system. Let us come to the speed governing system and the turbine model. Here I am using the reference, that is a book, Anderson and Schwartz, that is a power system stability book. The general purpose model as given in the figure, this is a figure, I will tell you, this is a figure, there is a general purpose speed governing system. Here you can say this is a governor and the pilot valve transfer function, and here the PM naught is going to be compared with this, and then we have some limiter P max, but we cannot increase the P max so much. So there is a gate and steam valve dynamics is noted here, and then here steam bowl, and then it is having transfer function, and then it is coming here through the it is reheater, and finally it is PM is coming here, that is compared with your electrical, and this is your oscillating power, whether it is positive or negative depending on if the power is increased or decreased here compared with this one. So this is a general purpose, and again this model I will explain when I will be discussing the load frequency control, because in the load frequency control we have to see that's how this governing system is acting to take care of any change in the load and if there is any disturbance, suppose there is a severe increase or decrease in the loads, how it is going to take care of those things. So in the next module we will discuss completely about all these blocks. As I said, here we can have the dynamics here, this whole dynamics. Now you can have the different orders, means for this you can see how many transfer functions you are going to take. You can see the dynamics means here this one is a one order, one variable x1, you are having another variable here x4, you are having x5, and you are having here x6. So here you are going to have 1, 2, 3 and 4 again differential, first order differential equation for the governing system itself. So again that will be included for each machine. So if you are using one machine, so the number of differential equation for excitation system plus the model of machine, if you are using third order model or fourth order model, that differential equation, and then the governing system model, so 4 equation here. So the total for one machine, the whole total, it may go up more than 12 to 15 differential equations. So you have to include in your transient stability program for accurate analysis. So let us see the load model, and that load model is also included in the transient stability program. As I said, the loads are represented by the impedance or voltage dependence or the dynamics of the load must be included in the transient stability program. So 3 classical static models of load, that is the voltage dependent, generally utilized are, first one is your constant PQ model. We know this P is nothing but your VI cos theta, theta is your power factor angle. This theta is your power factor angle and cos theta is the power factor, as we know. Now if here your load are independent of voltage variation as well as the current, then we can say your P is your constant, and similarly your Q will be also constant because this Q is nothing but your VI sin theta. So your V is constant, I is constant, means your load is independent of voltage and current. So that we can say your P is constant, and that P and Q is normally it is taken in the load flow. Load flow we take P and Q constant, we never take the dynamics of this, even though in few load flow analysis people are going to consider the voltage dependent load as well, but normally it is the constant P and Q loads are considered for the load flow analysis. So this is your constant P and Q, and it is represented as how much megawatt, and here it is written how much MVAR, and we have to include in your load flow analysis or you want to include in your stability program. Another is your constant current model. In this constant current, here the voltage is varying but your current is constant, so this P is called the proportional to voltage. Similarly your Q is also proportional to voltage. So the P and Q loads are proportional to voltage, and this type of loads are normally the converter loads, where the current normally, again different type of converters are used. For let's suppose you are using a converter in HVDC system, then the current in this line is always constant and we keep on changing the voltage. So it is possible that we can change the voltage. Your load, if it is given for a given load, if you want to feed the power, varying power there, the current can be constant and the voltage can be changed so that you can give the variable power to that one. So here in this one, the P and Q, that is real and reactive. P is your real power, Q is reactive power, that will be proportional to the voltages here, this equation as well as this equation. Third type of load model is called the constant impedance model, and in this the impedance of the load is constant. Means for example, let's suppose you have here a bus and there you have a resistance and here, and this is your impedance. This is your Z and Z is constant. So what will happen? What will be your P and Q here? That will be nothing but, if you write this P here, it is your V square upon here Z. Basically here the real power of this, and here it is the real of Z. So what is this? This R and here Jx, they are constant. So the impedance is constant. So I can write here V square upon R. So if the terminal voltage here of this bus is changing, the power drawn by this load will be also changed. So the real power will be now proportional to the V square. Similarly, your Q will be your V square upon X. So X is constant, so I can say Q is proportional to your V square. So whenever the voltage is changed, reactive power as well as the real power drawn by that load will be changed. So we have to take, if you have a load like this, for example, a simple bulb, that is a simple resistance. So you can see when the voltage is less, it gives less light. What does it mean? It means the energy dissipated in that bulb, that is the current, this R is constant, so the power by that simple, what is the bulb? Bulb is your resistor here, simply. So if the voltage of this bus is changed, so your power that is taken here and that power is converted into light. So the light power is reduced, means here V square upon R. So R is a constant, here V is changing, so here the power will be less. If V is reduced, if it is more, so it will grow more. So this type of load is basically called the constant impedance load, and the resistance load is one of the very popular load that is used, that is for lighting purpose. So we can say your real and reactive powers, they are proportional to V square here, and that can be included. A general expression, again for all these three type of loads, as we know, that's in any area, any distribution system, any transmission system, loads are the combination of all these three varieties. Means it is a constant, it is proportional to voltage, and also it is a proportional to the voltage square. So the general purpose expression for the composite loads, we can write this real power will be summation of your A naught, that is the factor contributes to your here, that is independent of voltages. So it is your constant load. Then we have another that is a proportional to voltage. So this is A1 is a proportionality constant, and your A2 that is your voltage square here. This is not here, this is a square. So similarly we can write for the reactive power. So we can include all these three proportionality constant here, means I can write here that is a P is equal to your A2V square. Here I can write the Q is equal to your A2V square. Similarly we can write for this case P is equal to your A1V, Q is equal to your A1. Here we can have a different, basically they are not constant, so A1 B1 here I can write, and here I can say P is equal to your A naught and Q is equal to your B naught. So here we can write this is your B2 square. So we can write another, because here B1, B2, B naught are the different, then because the reactive power is a different. So we can write the different coefficients. So the ever model assume the negligible frequency variation. So in this load model, we have not taken into the account of the frequency change of the system. It is only the voltage. So it is not taking the dynamics of the variation of even the voltages. It is only again this static equations that we have taken, and depending on the various loads we have formulated this. Now again there are several methods and several books, references they have suggested, like IPRI of USA suggested the use of following general model of the load, and they have used this P is nothing but your P naught. This is now multiplied by V divided by V naught. Here V naught is your nominal voltage, here it is a frequency, nominal frequency, and what is your system frequency. So if your system frequency is changing, so this P will be also changed. So this is now a general purpose. So here there are the exponent, there is the PV, here it is a PR. Similarly here we have the QB and the QR. So this is a PR is the exponent of this term, and here PV is the exponent of V, actual voltage divided by the rated voltage. Now these coefficients are exponents here, PB and PR. Similarly here QB and QR for the reactive power can vary, and the different values are given for the different type of loads. So this means these coefficients are basically taken from the Taylor's book on the voltage stability, that is a table 4.1, page 73 you can see. So for the various here, for example, just I will tell you, if PB is equal to 2, Pf is 0, Qv is equal to 0 and Qf 0, it is nothing but a simple resistor. Means what does it show? It shows that your P is nothing but your P naught, here V divided by your V naught, here your square, and your Q will be now 0. So it is a simple real load that is a resistive. Its voltage is changing, then we are getting the different power output. Suppose you are having a voltage, a bulb, let's suppose simple resistor here R, and this is giving your 100 watt bulb. This is your bus, this is your resistance. So it will have some value, and this 100 watt it is giving at, let's suppose, 220 volt. Now if the voltage is changed, then what will happen? It will be 100 V divided by your 100 at 220 volt, sorry, and then it is a square. So if your terminal voltage is 220, then it will be unity and it will be again 100 watt. But if voltage is reduced, then it is, let's suppose, 200, then it is 200 by divided by 220 half square, then your output will be reduced. So it is a simple resistive load, and it is used just like a incandescent lamp, simple bulbs, or it can be used in the heaters. Heater is also resistive filaments. For smaller loads, they suggested that the PV value should be 0.1, PF here is a 2.9, QV it is a 0.6, and QF is again negative here, 1.8. What does it mean? It shows that for motor loads, no doubt it varies on the voltage, but it is more variation is more on your frequency, that is 2.9. This is huge contribution in this. Means if you see here, I use this curve here in the P, this value is very small, this is very high, so this ratio is very dominant. And thus for small loads, here they suggested this value can be taken. For large motor, again you can see these values are very small, because the small motors are very much fluctuating with the change in the voltage and frequency. But large motors, here you can see this factor is very, very small, this is also reduced, here they are also reduced, and this is also reduced. For the fluorescent lamps, here you can see this, it is 1, PF is also 1, means it depends upon frequency as well as your, means here this P, it is your P naught, that is your V upon V naught, again unity, multiplied by your F upon F naught. F naught is your rated value at which this P naught is given. So you can see now it is changing with the voltage as well as the frequency. So the fluorescent lamp is very sensitive to the frequency of the system as well. Room air conditioners have now PV is this, PF is this, and this. Basically all this they proposed with the different tests, different simulations, different measurements. They suggested for the various loads you can take these factors for your various studies. To model the dynamic loads, as we saw that static models which we discussed earlier, they are insufficient to capture the voltage dynamics. They are simply the variation of voltage, but there is no, if the voltage is changing with the time, how they are going to affect your stability of the system, and how we can analyze what will be the actual behavior of the system. Main purpose of the transient stability or any program that we can reproduce, we can know the exact behavior of system by simulating. So the simulation we have to ignore as much as possible the assumptions. So to include this voltage dynamics, we should include this dynamics of the load as well. So a major portion of this dynamic loads are the induction motor loads. As I said, it is almost 70 to 80% loads are the motor loads, and mostly they are the induction motors, which has a significant effect on the voltage stability. So following model of the induction machine has been used by the Zayed and Taleb. They used in the IEEE Transaction and Energy Conversion Volume 6 in 1991. They just suggested that we can take this Vm upon dt, they have taken the time constant. So where this Vm angle is the voltage, this is angle Vm is the voltage behind R plus Jx. So they use here, you can see they use another two dynamics of the voltage as well as the delta that is interrelated. So we can have this basically solved using these dynamics as well, where this omega is your rotor speed, mm is the moment of inertia of induction machine, TO of the open circuit transient time constant, xs and x prime are the steady state and the transient reactances, PM and QM are real and reactive power drawn at the internal node of the motor, and TL was the load torque, and that was given as A naught plus B naught omega R plus C naught multiplied by omega R square, where the omega S is omega naught plus phi S, where omega naught is synchronous speed and phi S is the phase angle term of voltages. Two composite dynamic load models have been used for the stability studies. The load model suggested by Walbe in Segre report 1986, if there is a PS and JQS are the static components and the PD plus JQD are the dynamic component, then we can write this PS is equal to P1, that is a constant, QS we can also take a constant, but the dynamic component here, if we are having this component, then we can write the dynamic equation in terms of voltage and in terms of theta. So he suggested that we can take some constants here and then we can include those in your stability programs. Another model that was suggested, that is again by Dobson, Alvarado and DeMarco, they suggested in, and also in the M.K. Paul in 1993 IEEE transaction, he suggested the composite load consisting of static and dynamic components can be written as here the dynamic PD and here the dynamic reactive power that can have, even though this has an effect of your power factor, and this one here is the nominal MVA demand, this is it, and PF is the power factor that is also included, plus d theta dot plus a v dot, v dot here is the dv by dt. So here v dot is nothing but dv by dt. Similarly your theta dot is your d theta upon dt. So we can again we use this model. So let us see again the various methods for improving the transient stability. Already I have discussed few, but here we have to recap it. First, that we can increase, if anyhow, the inertia of the rotor. Rotor means rotating mass of whole system, not only generators. It can be generating mass of your turbine as well, because all are on the same shaft. So if that can be increased, then we can improve the transient stability. This is not possible during the operational stage, because once machine is installed, constructed, and it is going to deliver power, it is not possible to increase the inertia constant. It is only possible during the planning stage. So which size of machine you are going to install, that will, at that time you can basically change the inertia, that you can go for the larger, and again you have to see the efficiency and performance, that again depends upon the economy and the performance of the system. So this factor basically is not possible during the operational stage. Another is second option is the reducing the mechanical power input during the transient disturbances. As I said, here this is your generator that is rotating, here it is your PE, that is the electrical power is coming out, here it is your PM, and this difference here is your rotating. So if here this is equal to this machine will be rotating at the synchronous speed. So if there will be any disturbance, as I said, if there will be some disturbance, transient disturbance this side, that is it is your electrical side, what will happen? This PE will be reduced due to the fault, due to the tripping of the system, etc. So this PE will be reduced. Then what will happen? This difference, that is your PA accelerating power, it is your PM minus your PE. So this value will be positive, and this will cause acceleration of this machine, and thereby it will increase the internal angle of the machine, and once it is increasing, then it may even lose the synchronism if it is keep on increasing. So what we can do to reduce this, if anyhow we can reduce this, as in the previous case we saw that the PM is constant, but it is not so. If we can use some fast valving or speed governing action, then we can, during the disturbance, we can reduce this. So this accelerating power can be reduced so that the severity of the transient of the system will be minimized. Thereby we can improve the transient stability of the system. Third option is the increase the electrical power output. Means, as I said, during the disturbance this will be reduced. So what we can do, if anyhow we can increase this PE, so again the oscillating power will be minimized, and therefore here we can reduce the delta angle of internal machine, that it will be again minimized, and then we can improve. Now to increase this, it depends upon the several factors. We already wrote this PE, it is your nothing but your EF, terminal voltage, divided by here X, that is X is composite reactance including transformer lines and between the two buses here, and here it is your sine delta. So first one is that to increase this option, that we can increase EF as well as the VT or any one of that. So increase in the generator and or the terminal bus voltage, so we can increase the PE. For that we have to have the fast acting voltage regulator for increasing this EF, that is excitation voltage. Then we have to fast acting voltage regulator excitation system, that will increase. Another is to increase this VT, it is not in your hand. It is very difficult to control unless until you are having some extra device, and that device is nothing but your FACS controller, any shunt elements, you can say shunt capacitor or static wire compensator or static compensator, that is StatCom, that can be used to improve the voltage of this machine, terminal voltage, and then we can increase this. Another is disconnect the reactor, because you know most of the transmission line, the big transmission lines, here is a big transmission line, they normally use the line reactors. So they absorb the reactive power. So anyhow during that fault, if you are going to trip this, so what will happen, the voltage here will be increased. So disconnect the reactors to increase the PE. So these are the three options for again increasing the PE, and that is related with the EF and the VT increase. Another approach is to reduce the transfer reactance, that is X. That can be done, again reduce the reactance of machine, which is not feasible. Again I said there is, again it is only in the design process, and there is a lot of pros and cons for the higher and the lower values. So it is a compromise between what value you are going to take. So once it is designed, it cannot be changed. Another is that we can use the series compensation. We can use some capacitor here series, then the effective X will be reduced, and then we can reduce the transfer reactance. If reduction of this means it is a more PE. Another, we can also use the shunt compensation. Some of the shunt compensation they can also regulate in a such a fashion that the effective X can be changed, and then we can use that. Now another is that reduce the difference between PM and PU by using again the artificial loads. Means here we want to reduce this PA, means we can use some dynamic resistors, and again here that is a PM minus PE. So we can increase this PE during the disturbance by using some resistors. So that is called electrical braking, and dynamic resistors are used for that. Or full load rejection, that is not preferred, means we can reject completely load and then we can use. Another is the reduce the fault clearing time. As I said, in this angle here, if this machine is operating here, then this fault clearing point, if you are always try to reduce by acting fast protecting system, then again your system stability will be improved. Means that can be achieved by fast acting relays and circuit breakers. If you are having HVDC system connected with the system lines, then HVDC control actions can be taken, and then also at the same time FACS controller can improve the transient stability equally well. So if these devices are present in the system, then along with those devices if you are going to use, then it will be improved. So these are the basically the various transient stability methods, and that basically those are used for the improving the transient stability of the system. Thank you.